Welcome back to statistics. Suppose I told you that I could hit 80% of free throws standing from the free throw line. You might justifiably be skeptical, and so you challenge me to a test, right? We go out to the court, and maybe I shoot, let's say, 100, and suppose I made 78 of those. Would you be willing to call me a liar? I mean, 78 out of 100, that's 78%. You said 80%. You didn't make that. Most people wouldn't be willing to accuse me of being a liar in that case because, you expect a certain amount of variation. Maybe it is true that I hit on average 80% of my free throws, but you wouldn't be too surprised if in some particular set of 100, I only hit 78 because if we shot another 100, I might hit 82. You don't expect exactly 80 out of 100, even if I did truly shoot 80%. That 80 out of 100 is what would be true on average. In the same kind of way, think about a different example. Um, think about the number of newborns that occur on the various days of the week. Say at some specific hospital, let's say. So you might, keep track of this for a year or two. You would record the number of newborns that happen on Mondays. You would record the number that happen on Tuesdays. You would record the number that happens on Wednesdays, Thursdays, Fridays, Saturday, and Sunday, and so on. And the question is a newborn sort of equally likely to be born on any day of the week? If you just kind of think about that for a second, you might be inclined to say, well, yeah, newborns don't know what day of the week it is. They should have no reason to prefer Monday versus Friday or Saturday or any other day. So you might expect that, about 1/7 of all newborns are born on Mondays, 1/7 born on Tuesdays, 1/7 on Wednesdays, and so on. Turns out, though, that if you look at the actual data, and this has been done many times, if you look at the data from practically any hospital, you'll find that it's not quite 1/7 all the way across. In fact, there's a noticeable dip in births on Saturdays and Sundays. And of course, once you hear that, you probably realize the reason right away. Many of the births in hospitals are, not only attended by doctors, but are induced, or they are, a result of a cesarean section or something like that. And so the reason that there are fewer births on weekends is because doctors like to take the weekends off. It's not the newborns that are taking the weekends off, it's the doctors. But this would be another kind of situation like the basketball situation in which you would look at sample counts and compare them to some like, expected distribution. You expect 1/7 of all births to occur on any given weekday. Do they really? You expect on average 80 out of 100 of my free throws are going to hit. Do they really? There's a statistical test that addresses this question. It's called the chi-square goodness of fit test. It compares whether sample data are consistent with some pre-existing distribution that you would expect the data to follow. And so in this short video, I want to show you the basic ideas of the chi-squared test and work through an example. Let's check it out. So introducing chi-squared tests, testing the distribution of categorical data. That is one thing to mention here. The chi-squared test sees whether categorical data follows some sort of predefined distribution on the categories. I want to use an example about voting behavior, particularly voting behavior in Florida, to sort of motivate the discussion here. My basic question is, are voting patterns in Florida consistent with party identification? Florida is a good state to study this question because primaries in Florida are closed. That is, if I wanted to vote in, say, the Democratic primary, I would have to indicate on my registration that I was a Democrat, and only Democrats are allowed to vote in the Democratic primary. Similarly, only Republicans are allowed to vote in the Republican primary, and so on. So, not every state is a closed state. Virginia is not. You don't have to declare a party identification in order to vote in a primary. You can't vote in both the Democratic and Republican primaries, but you don't have to be a, you know, card carrying Democrat to vote in the Democratic primary, and are, likewise for Republicans. So, but in Florida you do. And the voter registration rolls in Florida can be used to give a breakdown of the fraction of the registered voters who identify as either Democrats, Republicans, or some other affiliation. And here you see the data from the registration rolls for the November 2020 presidential election. Florida finalized those rolls on October 6th. There were over 14 million voters who are registered in Florida. And as you can see from the data, about 36.72% of those are registered Democrats. Another 35.79 are registered Republicans, and the remaining 27.49% are identify as other. The other could be either just independent, or you also have all the known third parties like the Green Party and the Libertarian Party in that category as well as some other even lesser known parties. So when I ask whether voting patterns are consistent with party identification, what I mean is this: um, you know, would all the Democrats vote for Democrats? Would all the Republicans vote for Republicans? And would everybody who doesn't identify as a Democrat or a Republican vote for some candidate who wasn't a Democrat or a Republican? That's what I mean by consistent. So, in other words, if the voting patterns were consistent by this definition, and you had the election tomorrow, the election is actually in a week from today, but if it were, in any case, if you counted up all the votes and voting was consistent, you would expect about 36.7% of the votes to be cast for the Democratic ticket, 35.8% about for the Republican ticket, and 27.5% almost for the various third party candidates or write in candidates or none of the above. I'm not sure. Is that what actually happens? Well, of course, we won't know till election day, but we can use sample data to make some inferences about this situation. So here is a CNN poll that was done between October 15th and October 20th. So that was after the registration period closed in Florida. And the sample was from the set of registered voters. So our population here is the same as the population we discussed in the previous slide, registered voters. In the sample of 906 registered voters in Florida, we find that 435 of them plan to vote for the Democratic ticket, 417 plan to vote for the Republican ticket, and 54 plan to vote for some other candidate. So those are our sample statistics. I would point out that going back to the previous slide, those numbers 36.72%, 35.79%, 27.49%, those are actually population parameters, right? Because our population here is the set of all registered voters in Florida, and we've got the list here. These numbers were taken from an Excel sheet you can download from the Florida Division of Elections. So these are population parameters, whereas the counts I'm reporting from the poll are, of course, sample statistics. Now, if you look at that, especially look at the other category, 54 out of those 906 some odd voters claimed they were going to cast their vote for another candidate. If party identification was consistent with voting behavior, you'd expect 27.5% of the sample to say they were voting for someone else. But 54 is nowhere near 27.5% of 906, right? 20% of 900 is 180. And we only got 54. So far less than 27% of the other identifying voters actually cast votes for the non-major party candidate. And so it doesn't look like the voting behavior in Florida is really consistent with party identification. But of course, we could argue about this a little bit, right? Because this is just a poll after all. We only sampled 906 voters out of more than 14 million registered voters in the state. And a skeptic could say, well, yeah, we didn't get 27.5% voting for a third party candidate. We only got, 54 out of 906. But that's just normal sampling variation. We've got a sample from the population, randomly picked. If you picked another sample, you'd get a different number. And it probably wouldn't be 27.5% either, but it might be closer. And, in any case, the skeptic says, I think the sample results we got from the poll are completely consistent with those registration records. Well, are they? A chi-squared goodness of fit test really puts that question to the test. And it basically takes the skeptic's argument seriously. It asks, how consistent are those counts from our poll vis-a-vis the percentages from the registration record? It is a significance test. Like other significance tests we've seen, it has a null hypothesis. In this case, the null hypothesis is that the sample counts are consistent with the given distribution, with the distribution from the voter roll. While the alternative hypothesis is that the sample counts are not consistent with the distribution. The null hypothesis is, of course, the position of the skeptic, right? Who's saying those sample counts are just completely consistent with our registration records. And the first step in conducting a chi-square goodness of fit test is to sort of take the skeptic at face value and say, all right, well, assuming that those percentages from the registration rolls really do reflect how voters behave, what the voting patterns are going to be, what counts would we expect from a poll of size 906? And that's really not too difficult to think through. I've got some equations up here, which I'll talk about in a second, but let me just kind of flip back in the slides for a second. You would, if voting behavior was consistent with party identification, you would expect 36.72% of the votes in our poll to be going to Democrats. Well, our poll was of size 908, 906, right? 36.72% of 906 is 332.6832. That's quite a bit different than the actual observed count for the Democrats, which was 435. So that is the basic idea of the chi-squared goodness of fit test. Calculate the counts you would expect if the given distribution really was controlling things, and compare them to the observed counts that you actually got. So let's go back a slide or two and look at the details of this. Again, the distribution that the skeptic is saying is controlling things here, the distribution from the null hypothesis, is that the proportion voting Democrat is the same as the proportion who identifies Democrat, so that'd be 36.72%. Notice I've written it here as a proportion rather than a percentage, and that's what we'll need to do in using the chi-squared test. Again, the skeptic would say the null hypothesis says that uh, the percent who vote Republican will be the same as the percent who identify as Republican, and that would be 35.79% or 0.3579. And again, the percent who vote for a third party candidate would be the same as the percent who identify with something other than one of the two major parties, and that'd be 27.49%. So, assuming that those percents really were operative, really did describe the way people voted, how would a poll of 906 individuals break down, would you expect, right? Well, you would expect 36.72% of the individuals in the poll to vote Democrat. And again, that's that 332.6832. You'd expect 35.79% of the 906 people in the poll to go Republican. That's the 324.2574. And you would expect 27.49% of the poll to vote for a non-major party candidate. So that would be 906 times 0.2749 or 249. And so we compute those expected counts and we compare them to the observed counts. To the extent they're different, right? That throws some cold water on the skeptic's claim. The skeptic is claiming that, party identification is consistent with voting behavior. If that were true, you would expect the observed counts to be a lot closer to the expected counts. But the skeptic has an answer here too. He says, well, okay, I see the differences, but maybe these differences that we're seeing between the observed and the expected counts are just due to random sampling variation. Again, we've got a sample of size 906. That's not huge, especially compared to the 14 million voters there are in Florida. Maybe these differences are just what you would expect by random sampling variation. Maybe they're not, in other words, statistically significant. Well, the chi-squared test takes on that question head on. In order to carry it out, we have to build a test statistic. The test statistic for the chi-squared test focuses on the differences between the observed and the expected counts. For each category, you take the square of the difference between the observed and expected counts, and you divide by the expected count. That's called the chi-squared value for that category. And we'll see an example here just in a second. So each category will have a chi-squared value, and the chi-squared test statistic is just the sum of those chi-squared values over all possible categories. So what does that look like in our example? Well, we have three categories, right? Democratic, Republican, and other. You see the observed counts there for each category. You see the expected counts there for each category. And you see the chi-squared value for each category. And that was those chi-squared values were computed just using that formula on the top of this slide for each category. So the chi-squared value of 31.4676 is equal to my 435 minus 332.6832, the quantity squared, divided by 332.6832. And similarly, the chi-squared value for the Republican category is calculated in the same way, and also for the other category. The larger the chi-squared values, the bigger the deviation between the expected counts and the observed counts. Notice that the deviation is largest for the other category, right? That's already giving us a clue that something's happening in there. The folks who don't identify with either the Democrat or the Republican are not voting for a third-party candidate nearly as much as we would expect them to. They're probably voting for either Democrats or Republicans. In any case, the test statistic is the sum of the individual chi-squared values. So there you see it, the 31.4676 plus the other two values there gives us a chi-squared value of 210.7609. So how do we compute a p-value? Well, first of all, a little bit of theory comes in here, and it involves a new distribution for us, the chi-squared distribution. The theory tells us that if the null hypothesis is true, which we assume during a significance test, then the chi-squared test statistic follows a distribution that we call the chi-squared distribution with k minus 1 degrees of freedom, where k is the number of categories. So for our problem here, it'll be 3 because we have 3 categories, and the degrees of freedom, therefore, would be 2. Remember that higher values of the test statistic indicate observed counts that are more inconsistent with the null hypothesis and in favor of the alternative. So that means that the p-value for a chi-squared test turns out always to be a right tail area in the chi-squared distribution. Here's an example, and this is actually the example for our problem here. Our chi-squared value was 210.7609, and there you see the chi-squared distribution with 2 degrees of freedom because we have 3 categories. And the p-value turns out to be extremely tiny, 1.714 times 10 to the minus 46th. It's the right tail in that chi-squared distribution starting at our test statistic. That is, in other words, if I wrote that out, that would be a 0 followed by a decimal point, followed by 45 more zeros, and then 1714. This is about as strong as evidence gets, right? We have essentially conclusive evidence against the null hypothesis and in favor of the alternative. So again, p-values mean what they always mean. The smaller the p-value, the stronger the evidence against the null and in favor of the alternative. Voting patterns in Florida are not consistent with party identification. And what we see by looking a little more deeply into it, into the chi-squared values for each category, is that more people vote for major party candidates than we would expect from party affiliation in the voter registration list. And so that's our little introduction to the chi-square goodness of fit test. It, like the two sample t-test or the one proportion or two proportion z intervals, are very commonly used inferential tools in statistics. And we'll have a little bit more to say about it going forward. In the meantime, take care, and we'll be talking at you again real soon.